So good time of the day, everyone. Welcome to the multiple workshop. Today, me, Ivan Nikitsky from EPIC, the European Photonic Industry Consortiums, and my partners of the multiple project will present you the results of the multimodal spectral sensors and the orchestrated deep models for integrated process optimization project. Just to give you a few words about the project before we start. The objective of this European project was to develop a scalable and highly adaptable broadband multimodal photonic monitoring solutions for production optimization with a breakthrough impact on production quality and efficiency of production. This project includes 13 industrial partners from all around Europe and supported with 3 research and technology organizations spread all around 9 countries. With a total budget of over 7 million euro and the length of 3 years, this project will now come to an end at the end of this month. So the 16 partners of the project include the technology center IMEN, the software partner Abraya, as well as the IRIS Technology Group and IMEC in Belgium, Photon Focus, camera manufacturers, Tenorix, Air Optics, the MRA Grupo Alava, Things02, us as a EPIC, European Photonic Industry Consortium, Tematis, SCM, the woodworking technology production, Royo, and Russula. As well as this project includes 3 end users or early implementers of this technology, which is a chocolate production factory Iotis in Greece, the French Lamnoir de Land, the production of heavy metallic plates, and Royo, the Spanish producer of woodworking production of furniture. And today's agenda includes the representatives of all of those partners. So we'll start with a general presentation of the full monitoring system by Roy Mendes from IMEN, followed up by Karsten Schneemann from Photon Focus presenting the hyperspectral cameras, and Christian Kerner from Tenorix presenting the spectrometers involved in the project. Paweł Klipczynski from Air Optics will present the laser-based gas analyzers, and Anton Garcia from Abraya will present the computing platform. At the end of this seminar, Jordi Melado Carretera from IRIS will present the early implementation in the wood production. Cesar Taboas will present the woodworking use case at Royo, and Luciano Dominguez from Russula will talk about the steel production use case. And with this, without further delay, would like to start this workshop on multimodal spectral sensors and orchestrated deep models for integrated process optimization. And with this, I pass the word to the project coordinator, Roy Mendes. Hello, Roy. Whenever you're ready.
Yeah.
Whenever you're ready, please share your screen, and we're ready to start.
Okay, I think you can see my screen now.
Yes, we're good to go.
Okay, so hello everyone, good afternoon. I will give a quick introduction to the project and highlight some of the results we have achieved. So the aim of the project is to develop a cost-effective, scalable, multimodal monitoring solution based on novel spectral sensors for optimizing different production manufacturing processes. So basically we have 2 pillars in the project. The first one is to develop novel spectral sensors that can provide new information regarding the different processes we have in the project. We focus here on cost-effective solutions, and we have developed hyperspectral cameras in the BIS and SWIR range, and also spectrometers. On top of these sensors, we have developed an edge cloud platform that allows us to integrate these sensors in an easy way in these production processes the edge part is capable to communicate with the sensors and translate the raw data in information. And in the cloud, we have different services to train deep learning models that we can then deploy on the edge, and also dashboards to show KPIs and different process parameters to the production managers. So regarding the sensors, the first type of sensor we developed are these compact snapshot hyperspectral cameras ready for volume production. So a hyperspectral camera differs from a standard RGB camera in the way they sample the spectrum. So instead of 3 channels RGB, we can have tens or hundreds of spectral bands. So for each pixel, we have like the spectral signature. And from this spectrum, we can obtain much more information than a standard visible camera can provide. There are different technologies for implementing this kind of hyperspectral cameras. So the standard ones are line scanning push broom sensors that integrate only one line of light at a time. And in these systems, scanning, moving the object with respect with the camera is needed. The other approach is wavelet scanning. Here we have like a tunable filter, and we can collect at each time only a single band. So to create the hyperspectral image, we also need some scanning, in this case, in the spectral domain. And the aim of the project is to develop and demonstrate the usefulness of this new technology based on snapshot spectral filters. In this case, the filters are on top of the pixels, so we can collect the whole hyperspectral image at once. And this enables, for instance, recording moving objects. Also, these cameras are much more compact because we don't need any dispersive element, any complex optical arrangement. And the main trade-off is that we have a bit less spatial resolution and also spectral resolution. But for many applications, these cameras provide a lot of benefits. The other kind of sensor we have in the project are spectrometers. We have developed organic electronic-based spectrometers for material sensing. These are really cheap solutions without diffractive moving parts, covering a wide spectral range from 400 to 2000 nanometers. And finally, we have laser-based spectrometers. These are high-end products with very high sensitivity and selectivity, and focus the wavelength of the laser in the specific range we need to detect a specific compound. With this technology, we can cover a wide spectral range from visible to mid-infrared. And from this spectral range, we aim to obtain a lot of parameters regarding, for instance, the composition, texture, temperature gradients of the products and the production processes we have in the project. So the key achievements result from the project are the development of 2 new cameras, one hyperspectral SWIR camera covering the spectrum from 0.9 to 1.7 micrometers, having 9 spectral bands, and also a dual aperture camera prototype combining a CMOS and InGaAs detector in the same camera platform. With this, we cover a wider spectral range from the visible to SWIR with 25 bands. We also have adapted 2 laser-based spectrometers for gas analyzers, one focused on acetone and another one focused on different compounds like CO, O2, and water that has been installed in a still working for monitoring a reheating furnace. And finally, the organic-based spectrometer has been adapted to monitor chocolate production, in this case, having 16 spectral bands covering the range from 1.2 to 1.7 microns. On top of these sensors, we have developed this edge cloud infrastructure. Basically, we have 3 layers: the sensor on the bottom, then some edge devices, and finally some cloud services. So the edge devices provide connectivity to these sensors, are capable to perform the analysis online and share the information with the cloud or other devices present in the shop floor like PLCs. We have adopted protocols common in Industry 4.0 like OPC to share in an easy way and integrate in an easy way these devices in the production lines. And on the cloud, we have developed services for model development, focus on hyperspectral and deep learning. We have a lot of high dimensional data from the cameras, and it's very important to manage this information in an efficient way. And also, we simplify the development and deployment of these models. And then we have the production services focused on the production managers that can show like time series data and KPIs. So these are the results. On the left, we can see here an example of an edge device connected to a camera. For the edge devices, we have developed a new computing framework that can help us to develop complex processing pipelines in an easy and fast way. So we can create like processing graphs, combining different modules among them, and also show this as an interface through OPC-UA. So any user can connect to the device and change easily the process parameters that are processed in this pipeline. The edge devices have direct connection to the cloud services, so we can send time series data, different process parameters that can be visualized and analyzed here on the cloud. And also we have direct connections to the cloud services for DevOps development, so the development of these deep learning models. Also in an easy way. So the images arrive to the cloud with a label. Here we can manipulate, modify the data sets, train or use some pre-trained deep learning models. When the model is ready, we can easily deploy it back to the edge for the online inference. And in addition, we have developed a client graphical interface that can be deployed in any PC on premises that can be connected to the edge device and show in real time the results to the operator. Regarding the applications, we have integrated this technology in 3 different use cases. The first one is steel manufacturing in a rolling mill. Second one in woodworking. We work with end user, a furniture manufacturer. And finally, in the food industry, targeting chocolate production. These use cases will be presented in the next presentations, but I would like just to highlight some examples of these monitoring solutions. So in the steelworking, we have installed the dual aperture camera to monitor the slabs that are passing forward and backward in the rolling stand. And with this camera, we are able to monitor 2 different parameters. So on one side, discriminate the steel alloy composition. They are working with different references, and we want to avoid the mixture of these references by human error. And for this discrimination, we use the visible range. The steel slabs emit a bit different. We have detected some peaks in the visible spectrum. And with a simple SVM, we can classify accordingly. And also with the same camera, we are able to measure the temperature. These slabs are around 1000 degrees Celsius. We have combined several bands in the SWIR range to provide robust measurement of temperature, reducing the effect of emissivity. In the woodworking use case, we have an application for detecting different defects in wood panel. For that, we have created a complex processing pipeline based on deep learning semantic segmentation models. And this pipeline is able to process images from 2 different cameras that are needed to cover a quite large white conveyor belt. The inference is running in real time, and we have quite good results regarding detection. Also, with these end-to-end deep learning models, we reduce the need of the complex pre-processing of the hyperspectral images that we usually have to calibrate, do some compensation and illumination, and so on. So yeah, this is also a bit simplified with this kind of models. And finally, for the chocolate production, we have integrated these spectrometers to estimate the viscosity and particle size in the conching step during production. And we will see later the results. So I think this is all from my side. So thank you for your attention.
Thank you, Roy. Great presentation. I hope you all enjoyed it as much as me. Just to remind everyone, so we have a possibility to ask questions to our speakers after each presentation. Just click on the raise hand button at the bottom of the screen, and I will give you this possibility. While you're looking for the button, I'll ask the question myself to Roy. Actually, after this successful implementations in woodworking, steel production, and food production, Roy, could you identify other industries that could benefit from this kind of solutions, multimodal quality control?
Yeah, I think there are a lot of industries. I think hyperspectral is mainly used for sorting. I think these kind of cameras can be adapted easily. Here we are also doing some tests in steel manufacturing, additive manufacturing. So we plan to use this hyperspectral camera in the suite to monitor the process and check the quality. Also, I think in agri-food, there are a lot of potential to use these cameras to estimate different parameters. So.
Okay. Yeah, Antonio, please go ahead.
Yeah, I also have a question about the future applications because you mentioned gas sensing as one of the applications for one of the devices. Do you think also liquids, I'm thinking, for example, in chemical industry, could be market in the future for at least one of the hardware you develop?
Yes, sure. I think the sweep range is quite useful in pharmaceutical sector, for instance, to detect the quality, avoid the mixtures of different compounds. So yeah, I think they also have applications.
And I have a second question that is more a curiosity. What was the most challenging part? Was any hardware development? Was the integration of all the solution? You probably have the overview of all the technology. So what was the main challenge for the project?
Yeah, I think it depends on the partner you ask. For me, I think the most challenge was probably the integration and demonstration in the end users. Some of these end users have very harsh environments, like the steelworking, also woodworking are lines that are producing almost 24/7, and we cannot interrupt this production to test or integrate our sensors. So yeah, in these cases, at the end, these are prototypes, are not still final products. So it was a bit challenged, but I think we did it at least partially in all the use cases. So I think we have some good results.
Okay, good. Any other questions? Roy, actually, as you present not only the project overall, but also IMEN, Could you say a few words on the involvement of Ayman in all those projects and yeah, the results achieved?
You mean the result from Ayman's side?
Right,
Okay.
right. Which part of this was covered with Ayman?
Okay, so we were the project coordinators, but we mainly worked in the development of the edge solution. So basically in the edge computing framework that is integrated in these edge devices. Also, we developed some deep learning models for some of the applications. This was not only covered by us, also shared with some other partners. But the cloud part, the edge part, sorry, was mainly covered by us.
Okay, okay. And just in a few words, what do you mean by these edge solutions?
So we provide a commercial edge device, basically hardware with Linux installed, and we develop like a framework, is kind of a library that allow you to create these processing pipelines. So you have models that enable the collection of data from the sensor, from the cameras, PLCs, and so on in an easy way. So we don't have to program anything again, just configure some text files. Then we have some modules that can run the inference, deploy these deep learning algorithms on the edge and running in real time. And then we have other modules that do the communication with the upper layers in the architecture. So we can send the results to a PLC through OPC UA or connect it to a cloud service through MQTT and so on.
Okay, okay. Yeah, I hope now it's clear for everyone because it's a very complicated solution altogether. We have maybe one last very specific question from you. It's in the chat from JS Kim from Panoptics. He asks about the temperature monitoring for the hot steel manufacturing that you showed. Which temperature will be the maximum, more or less, to measure with this solution and the resolution? I'm not sure.
Yeah, okay. So we target around 1000 degrees Celsius. We have calibrated the camera with black body we have here in Ayman that reaches up to 1300 degrees Celsius. So we know we can cover from 500 to 1300. I guess we can go even further, but we don't have an easy way to calibrate the solution here.
Mm-hmm. And with which resolution, more or less?
The resolution
Of temperature.
Yeah, I don't remember exactly. Below 1 degree Celsius, I think was the accuracy we obtained with the calibration, but I think we need further validation of the system.
Okay, okay. I think that answers the question. All right. So thank you very much, Roy. If there's no further questions, I'd like to pass the word to the second speaker that will show us the hyperspectral cameras in more details. Karsten Schneemann from Photon Focus. Whenever you're ready, Karsten, the floor is yours.
Yeah, thank you very much. My name is Karsten Schneemann. I'm a senior engineer at Photon Focus in Lachen in Switzerland. And today I'm going to present our hyperspectral cameras with a special focus on what we have done within the multiple project. So maybe in the beginning, a little bit about Photon Focus. So we were founded in 2001, so we are already a seasoned company. And since 2019, we are part of Atlas Copco Machine Vision Solutions, so within a larger company structure. And we have specialized in customer-specific modular cameras and development of application-specific modular cameras. And well, some of them are in the spectral cameras, but we also have a large portfolio of general machine vision cameras, high-speed cameras, high sensitivity cameras, etc. So maybe an overview on what I'm going to present. So first, I'm going to quickly recapture what approaches to hyperspectral imaging exist. Roy has thankfully already given a very good overview on how this, what the basic idea is of hyperspectral imaging. Then I'm going to show what sensors we used for the multiple project, what camera designs we used for the multiple project, and in the end I will show some of the application specific implementations that we did during the multiple project, with one example of the use of hyperspectral methods for inspection purposes. So again, the hyperspectral imaging, the basic idea of hyperspectral imaging is to have like with a color camera. I mean, there are monochrome cameras. There are maybe color cameras for RGB that most people probably know, and there are hyperspectral cameras that have more than just 3 color channels, but in principle an arbitrarily high number, depending on the application, of spectral bands that where they provide color information for every pixel in addition to intensity information. So there are essentially 4 kinds of classes of approaches to hyperspectral imaging. One of them is the push broom method, where one essentially uses a spectrometer. So in one direction, the image is spread out spectrally, and in the other direction, you have the normal spatial information. And that means in order to get a 2D image, you need to use some kind of scanning. Roy had a very nice little movie about what the basic idea is, how to scan over a work, a piece, like a device under test or so. Then there is another popular approach is hyperspectral sensors, which have a kind of mosaic, filter mosaic on top of them, to encode the wavelength information spatially. And this is the approach that was taken in the multiple project. Then there is, as a third method, there you can of course have several sensors, and many mobile phone cameras take this approach nowadays. In the early days, by the way, television cameras usually also just had 3 separate tubes in the early days. So you just have 3 or as many spectral bands as you want to consider. You have multiple sensors, and either with a beam splitter or they just sit next to each other, and you somehow have to re-register the separate images to form a unified single image. So the fourth one, the fourth class is what I would call other solutions, other approaches. So this is like with filters, adjustable filters, programmable, tunable filters, or filter wheels, and yeah, these are generally other solutions. So what's somehow important is if you want to have snapshot images, then essentially only the class 2 and class 3 on this slide are feasible, because in most of the other cases you need some kind of scanning or switching your tunable filter and so on, so they are not really suitable for snapshot imaging. So this is essentially the idea of what a snapshot imager looks like. as compared to a push broom, classical push broom multispectral imager. So here you see with a red crosses that one important thing is that such a camera is substantially simpler in its mechanical setup than a classical push broom spectrometer camera, because you essentially have just the objective dispersive element that splits the image into by wavelengths in one direction, and then you have the sensor in the end, maybe with color filters, depends. And then, of course, you need a sensor that has this kind of hyperspectral filter mask on it. So for RGB, this is usually called the so-called Bayer mask, which is a 2x2 mask for RGB cameras. And of course, if you have more spectral bands, you also need more filters. Yeah, so what we have used in the multiple project is a novel type of hyperspectral sensors manufactured or modified by IMEC. So these are sensors that have an array of interference filters on top of them. So dichroic filters and interference filters on top of them that are adjusted to transmit light in a very narrow wavelength range. So you can, on the left-hand side, you see the possibilities that this approach offers, that you can have a mask on your sensor that basically captures those colors or wavelengths that you are interested in your application. And they can be very narrowly selected, these wavelengths. Okay. So let me move on to the sensors. So the sensors that we have used for this within the multiple projects are two different ones. So one is shown here on the left-hand side, is a standard CMOS off-the-shelf NER sensor from CMOSIS CMV 2000 with this kind of filter mosaic on top that I showed in the previous slide. So there's for example, a 5x5 mosaic, which would give you 25 bands, different spectral bands that you can resolve. Then the other sensor shown here on the right-hand side is from SCD, the SCD Cardinal 640. That is an INGAAS sphere sensor, so it's sensitive in a different spectral range, starting at 900 nanometers and extending to 1700 nanometers, so into the near infrared range or the sphere range, shortwave infrared range. And there are different possibilities on what kind of filter mosaic you put on it. So there is for example, 4x4 with 16 bands, or 3x3 with 9 bands. Let me note one thing for the about this mosaic, hyperspectral mosaic approach. Of course, in the image processing afterwards, you the image you get out of such a sensor is not directly the scene that you are filming, but it's convolved with this filter mask. So you get a like you see the mosaic in the final picture. And so as a first step, you have to recover the intensity and the wavelengths information. You have to somehow separate these two types of information by a deconvolution algorithm. And there is IMEC also provides a software library for doing this deconvolution step, so that you have really separate color channels, that you have, for example, that you can still easily recover the total intensity and the average wavelengths, etc. So this is, if you will, this is kind of a drawback of this mosaic approach, but one which Roy actually mentioned in his talk. This is often an acceptable trade-off for many applications, but in principle, you lose a little bit of spatial resolution because you have this mosaic on top, and by recovering the image in the deconvolution step, you in theory lose a little bit of spatial resolution. So if you have a 1 megapixel sensor, monochrome sensor, the color sensor will have something slightly less than 1 megapixel resolution. Yeah, so this is the example of the sphere of the hyperspectral sensors. And so within the multiple projects, we developed 3 different cameras. And our modular system, the photon focus modular system, always works in such a way that you have a sensor circuit board with a sensor on top, then you have a processor circuit board, and we have an interface circuit board. And for all these 3, there are different options, and the basic idea is that you can freely combine these 3 options. Yeah, so for the multiple project, we had first an hyperspectral vis NIR sensor with a CMOSIS sensor, which basically goes on an own sensor board. Then we had a sphere sensor, the cardinal sphere sensor, a camera with just a cardinal sphere sensor. And as a third option, we had the dual aperture camera, which has both sensors in one camera. And so these sit on an individual circuit board, and the data is processed by, in this case, by Kintex, Xilinx Kintex FPGA processor, and streamed out through a gigabit Ethernet interface on the interface board. So this is how it looks mechanically. So such a camera. So on the left-hand side, you have the hyperspectral vis NER camera, which has only one sensor. And below the sensor, you have the processor PCB. And then you have 2 interface PCBs. This is in the case of 10 gigabit Ethernet. This, because of the larger magnetics for 10 gigabit Ethernet, this has 2 printed circuit boards. Then the sphere sensor is in principle similar, has a similar setup. However, it also needs a temperature controller because the sensor needs to be cooled and held at a certain temperature to get a good signal to noise ratio. And on the far right, you have the dual aperture camera, which features a board that can take 2 sensors on top, the CMV and the cardinal sensor next to each other. But the rest of the camera is in principle identical in all 3 cases. So note that in the middle example, the sphere camera, I have shown it with a 1 gigabit interface, which only needs 1 interface circuit board. Okay, so this is what the final camera then looks like. On the left-hand side, you see what how this stack of circuit boards is assembled into a camera, and on the right-hand side, you have the sensor PCB in its housing taken out. There's also a shutter in front of the sensor. This is used for calibration to just make the sensor dark and get the dark capture a dark picture. There's a mechanical shutter for this purpose, and so this would be the cardinal sphere camera, single aperture sphere camera. As you see here, as I said, the InGaAs sensors, they always need a tech controller, so temperature controller that has an individual board that essentially controls the cooling of the sensor. So this is how this has to be modified for the INGAAS cameras. Yeah, then one application that I'm presenting on this slide is for ATEX applications, so applications in an explosive atmosphere. This is for inspection of paintings, of wood paintings, where the solvents of the paintings can cause an explosive atmosphere. So this whole camera has to be included in a special housing that prevents any kind of electrical discharge or whatever from happening and igniting this explosive atmosphere. So this is also something that like a customer specific solution that we developed for ATEX environments. And what I'm showing here is the sphere camera, the single aperture sphere camera in this ATEX housing. And finally, the dual aperture camera that we have developed during the multiple project is shown here. So as I said on the second slide, this doesn't have a beam splitter of any kind, like a prism, a dichroic prism or something like that, but it's just two sensors sitting next to each other. And on the far left side picture, you see how this camera looks if you take away the front plate. So there is the PCB with the CMV 2000 sensor, with the CMOSIS sensor, which is for the visible and near infrared range, with a mosaic printed on it. And below it is the cardinal, SCD cardinal sensor, the INGAAS sensor for the sphere range, also with a mosaic printed on it. Both sensors have, for calibration purposes, as I said, feature a mechanical shutter to capture a dark image. And so in the end, you get this compact camera that has at the back side a 10 gig E interface for connectivity to the image processing solution, and a general I/O interface for example, the shaft encoder. So for scanning for scanning applications, you often need a shaft encoder to capture the exact position of your workpiece. So this is the last slide in my presentation, and it's an example of an inspection application that was done. So the task here was to distinguish cloth, textile materials between linen and wool, to classify, is it linen or is it wool? And just in the visible range, this is very hard to tell because most textiles are actually colored. With like whatever dye is currently fashionable, what color is fashionable. So if you want to sort them by their spectrum, you have to go to the near infrared and the sphere range, and this is what we have done in for this example. So there is in the middle there's a false color image that shows what the sphere image that has been captured looks like. So here you see that the coloring of the textiles doesn't matter anymore. So they look all somehow the same, and but you can tell slight differences depending on whether this is actually linen or wool. And then the far right picture, there's a classifier has been run on top of it to show which regions in space are covered by a linen piece or by a wool piece. And so this is one of the possible applications for hyperspectral imaging. And with this, I'm done, and thank you very much for your attention, and I'm open, of course, for questions.
Thank you, Carsten. Very good presentation. We have already a question for you from Andreas from Heft System Technique. Let me ask it for him. What is the shutter for? And I know those shutters only from lead salt FPAs, like low-cost thermal cameras.
Yeah, it's a similar. The idea is similar. So if you move to the sphere range, then you move closer to the thermal emission spectrum of your environment. For example, in this steel plant application, we saw that the thermal radiation has a large in the sphere band is very well visible, but of course also the thermal radiation of your whole environment. So usually if you want to get a zero picture, so if you just shut off the camera completely and don't look at any piece, work piece, then you still get some intensity just from background noise. And the shutter is there to just shut off the camera and make it as dark as possible, so that the camera is totally dark and the only intensity and the only radiation that you see is essentially the thermal noise that from your environment. Yeah, but it's similar to from the probably you're referring to long wavelength infrared cameras, like from what's the name, FLIR or something like that. There are cheaper ones have a shutter, and the more expensive ones, then I don't know why they leave the shutter away, but they have other means to control the temperature. And so yeah, it's not so much a question of cost, I would say. It's really a kind of a feature that you can use, but you don't have to use it, of course.
All right, thanks, Carsten. And I also have a question regarding, in general, the cameras involving the IMEC mosaic image sensors. Is this remains something that is specifically developed for multiple projects, or is it now widely available for all your customers?
So of course we have we are selling this. We are trying to sell this technology to. It's highly customer specific. So my answer would be it's highly customer specific. Of course, if we have if a customer has an application, then yes, we can sell such a sensor. Yeah. We would offer the customer such a sensor, but it always depends on the specific application.
Okay, I see. And in terms of multiple project, was it what was the impact for you at Photon Focus? Did it help you to reach out to those end users, maybe to other partners that you can make multimodal systems together with?
Yeah, I think that was a good thing about the participation. Our participation in the multiple project was that really the contact with end users and learning about what applications they have and what needs they have for their applications, because there's with technologies like this tailored mosaic sensors from IMEC, many things become possible that weren't possible before in the last years. And so I think there's a huge potential that, of course, we want to make use of. And I still think that there's only a very small part of the whole potential of this technology has actually been recognized by the end users yet. And for the future, there's a lot of really many applications, I think.
Okay. There is one more question for you in the chat also. Did you think about the alternatives to the in-gas detectors in the SWIR range, such as quantum dot Schottky photodiodes, for example, to overcome the limitations in cost and spectral range?
Yeah, of course. I mean, this is something where I would say, sure, if there's a discussion, will in-gas detectors at some point just go away and be replaced by example for the quantum dot detectors? Because these quantum dot detectors, of course, they have huge advantages. You can use standard CMOS technology more or less to manufacture the sensors. You don't need special technology. You don't have, in-gas is not the nicest material from a toxicity point of view to handle. So this is also something, and it's very expensive. Spectral range, as as you mentioned, is limited. So yes, if quantum detectors finally come into the application domain, I think there will be lots of applications that will adopt them because they have huge advantages in several factors. I don't think that they will, that InGaAs will completely go away, but yeah, there are certainly applications where these quantum dot detectors will replace InGaAs. But there will also be applications that currently are not possible for cost reasons, because these InGaAs sensors, they are significantly more expensive than for example quantum dot sensors, and so there are just some applications that would be interesting but are not possible for cost reasons, essentially. So yeah, of course, I mean, we are keeping track of all these developments, and but I think like specifically quantum dot detectors, probably from a technological readiness level, they are not there yet that you can offer off the shelf or a camera with them.
Right. I think that's the state of the art. Well, thank you, Carsten. And with this, I'd like to pass the word to our next speaker, Christian Körner from Synorics, who will present us the other important piece of multiple project, which are organic spectrometers. Christian, the floor is yours.
Okay, can you hear me?
Yes.
Yeah. So welcome to my presentation. I will talk about miniaturized spectrometers for material sensing, and I will first have a look on the company where I'm coming from, which is Synorics. I call it Synorics in a nutshell because I want to make it short. Our vision, I put the vision at the top. The vision is to positively impact people's life with material sensing, and this we do with our patented technology. The technology was spun out from the Technische Universität Dresden, with whom we are still in close cooperation. We're still located in Dresden. You see our headquarters at the picture at the bottom, with the nice Elbe River in the back. And we are quite international company. We have at least 6 nationalities, changing forth and back, but I think at the moment it's 6. We have a strong science background with 11 PhDs in science. We are still growing, currently around 40 people. And of course, we have more than tech. It's around 60% technical stuff, but also some business marketing, management and support, and so on. We're very interdisciplinary. We're not offering just the technology with the material sensors, but we're also including software, device physics, engineering, optics, also chemistry people, data science, and also others. So I will first have a look on the chip technology, which we have developed and also used in the multiple project. The technology is based on organic photodiodes, which is our patented technology. And based on those photodiodes, we built this chip, which you see in the middle. This chip has 16 channels in the sphere range, and the filter is directly included in the processing of the device. That's why it's very cheap to produce and also easily scalable. The chip has 16 well-separated channels with a detection between 1100 and up to 1800 nanometers. You see the sensitivity of those single chips, single pixels in the bottom right picture. Well separated in the target range. There's no optics or whatsoever included, so we have a very good temperature stability, no shifts or so in spectrum. Of course, organic electronics is always a question, what's the lifetime? But there's absolutely no issue. We have done accelerated tests, and there's at least 20 years of lifetime of those chips is possible. And we also have a positive benchmark from our partner ZEISS. They have tested our chips against state-of-the-art spectrometers, and they have proved very good results matching those spectrometers for certain applications. But we do not only want to supply the technology itself, but we want to make material sensing. As I mentioned at the beginning, that our vision is to impact people's life with material sensing. So we took the technology and built a full device around it. It's quite small, mobile, battery-driven, everything included, also the illumination. And via the cloud, you get measurement results within a couple of seconds. The device is built for contact mode, which means you have to put the device directly in contact to your sample. We have tested a couple of applications with the device, for example, the textile applications, which Carsten also mentioned before, that you can distinguish different textiles. Also agri and food examples. We are also looking into cannabis characterization. And in the bottom line, you see cleaning robots and also paper and cardboard characterization. And we have also been looking into beverages, like, for example, beer. That was about the forward. And now I want to talk about what we did in the multiple project and how we used our sensors in the multiple project. So our job was to exploit the technology, which is a little different from the hyperspectral imaging cameras, which you heard before. So not for all of the problems, you need especially the imaging. And that's where we come into play, because our sensors can be much cheaper. And if the imaging is not required, our cheap solution can be beneficial. And in the multiple project, that was the chocolate production, at least part of the chocolate production use case. Because the problem there is to detect the particle size and the viscosity during the conching process. And this process means that the sample which you're looking at is melted chocolate. So for melted chocolate, there's no spatial information at all. So you can also discard the imaging and just use multimodal sensing device. So this is a sketch of the setup. You have seen a photo before in Roy's talk. We just made a bypass in the conching machine, and the target was to build a sensor unit and put our sonoric sensor device inside. All the integration part was done by Iris, and there will be a talk later by Jordi. So our job was to modify our sensor unit that it can be integrated by Iris in the full device, also with the much more powerful illumination unit. And as I said before, our device is optimized for contact measurements, but you cannot make a contact measurements with liquid chocolate in the bypass. That's why we modified also the device to allow for distance measurements and also to measure at a tilted angle. So the result you see on the bottom right side, this is our sensor device, which includes also more sophisticated optics, and it was optimized for this 10 centimeter distance and then integrated by Iris. With that, I already come to the end. The multimodal sensing device is a good alternative for use cases where you don't need necessarily the imaging functions because you have homogeneous samples, for example. And with our technology, we can do many more applications. As we also heard before, cost is always an issue. And if high costs cannot be afforded, then the low-cost multimodal sensing can be a good solution. The insights into the chocolate characterization will be given by Jordi later on. that's at the end of the talk. Just wanted to have a small teaser. We are hiring. If you know someone, cloud software engineers, sales manager, business development manager, just give them a hint. We're looking for those people. And with that, I want to thank you for your attention and all the partners in the Great Multiple project for collaboration.
Okay, thank you, Christian, for sharing all this. That was very exciting, and it is now open for questions from the audience. And while you're searching for the raise hand button, I'll ask my own question. What is actually the most important outcome of this project for you, Christian? I mean, for Synorix, did it help you to contact the users, find new partners, maybe finalize your sensors, optimize them?
So as also Carsten mentioned before, it's always interesting and necessary to have the end users, because the end users have the problems for our solution. If you have just a solution, not the problem, then it's always a problem to get into the market. So for us, it was very interesting to learn about this chocolate use case, to see the results from obtained by Iris, how our sensor performed in the chocolate characterization, but also the integration of distance measurements in our sensor. That was very important for us because it opens a quite large range of new applications where we cannot come in contact with the sample.
Okay, fair enough. Any more questions? Antonio, please go ahead.
Yeah, thank you, Christian. I saw that in the scheme you presented, you shared the illumination with your sensor and the ED sensor. Was an easy integration, or was it difficult to find a good illumination source for both detectors?
To be honest, you have to ask this question to Jordi, because they did the integration. I guess it was not so easy to integrate the two sensors with the one illumination unit, but I will leave the word to Jordi later.
Yeah, okay, we'll come back then to this in the manufacturing case. Thanks again, Christian. With this, I will pass to our next speaker, which is Paul Klikczynski from Aeroptics, which will present the laser-based analyzers for us. Paul?
Yes, hello, everybody.
Hello. Yeah, just go on the full screen and
yes, okay, I hope you can see my slides. So, good afternoon, everybody. My name is Paweł Klikczynski, and I'm from Aeroptic, and I will talk about laser-based gas analyzers and our role in the project. So first of all, starting a few words about our company. So we are a SME based in Poznań in Poland, and our specialty is laser-based analyzers for different industrial applications. And we have them in different configurations, starting from in situ, so the analyzers that work directly in the process, so without any sample conditioning systems. And second group is the extractive analyzers that are developed and made for extractive analysis, some more like gas chromatography for petrochemical applications. And last but not least, open path analyzers, so the analyzers that measure in the open space on the long distances, up to 1 kilometer distance is possible. So for fugitive emission monitoring applications. And they are all based on the laser gas absorption spectroscopy. So the principle is as follows. So we have typically a transmitter and receiver units that are mounted on opposite side of the process. And the process can be anything from, say, a couple of centimeters up to 30 meters. And as I mentioned, also 1 kilometer is possible for the open path systems. And we measure the molecule of interest or the molecules of interest using the absorption spectroscopy. There are some schemes that we apply to enhance signal-to-noise ratio. That I will not go into details, but basically you follow the Lambert-Spears law of absorption. And in using this method, you are able to detect very small amount of different analytes, and you can do it very fast. So the response time of such analyzer and sensitivity of such analyzer is very, very, very good. And this was our aim in the multiple project, to try to apply this technology also for some specific use cases. So one being the steel industry, and the second, wood industry or furniture industry in general. And so using the lasers, one is able to measure very selectively, because the laser light is very narrow band compared to the spectral width of the molecules of interest. It means that we can very precisely tune our laser's frequency into the absorption band of the molecule. So it's a very selective method. And you can do it by tuning the current of the laser. You can do it by tuning the temperature of the laser. So starting from the typical applications, you can have, for example, combustion control. So this is one of the tasks in the project. But in general, starting from what was already known, so that we have a typical boiler application in any, say, power plant, or can be also a petrochemical plant. There is always some energy needed, so there is always some fuel burned for different purposes, and then you have to optimize this burning process. And typically it was done by measurement of the oxygen and sometimes carbon monoxide directly in the boiler, because then knowing these components, you are able to control your fuel and air ratio. And by means of that, you can have a very efficient combustion process, which means you will use less energy, and you also have a better product, say, for petrochemical applications. And so this is what was already known. But now the idea in the multiple project was that why not applying this for the steel plant application? So very demanding application with a very harsh environment, because while you have a 700, 800 degrees in the boiler, you are reaching 1300 degrees, so 1200 degrees C in the steel reheating furnace. And this was our challenge in our task in the project, to develop the analyzer, which can measure in this very harsh environment, and moreover also measure more components than just oxygen and CO. And so we have been developing laser-based analyzers made on multispectral beams. So not only one laser frequency, but several wavelength frequencies. They were supposed to be deployed on the reheating furnace, so along the wall. So this is the sketch of the actual field site. So we had a very long reheating furnace, and several sensors. So in fact, 3 gas analyzers were installed along this line, and also on different levels, because you have different sets of burners, to try to see if we can optimize the combustion process. Or in the other words, if we can see some characteristic of the combustion gases in the space or volume above the burners. So this is a picture of the installation. So this system was deployed after development in 2021 already. So we have almost second year now of operation of our analyzers there. And they are measuring oxygen, they are measuring the temperature, they're measuring the methane, water vapor, and the carbon monoxide, of course. So what we can see, so in the past, the customers were using very simple oxygen sensors, being, say, typically a zirconia. But now with the laser technique, we are able to monitor in the real time. That's what I have to mention also, that this technique is measuring constantly, 24/7. So there is a continuous output of the gas analysis with response time of 1 second to the end user. So now this was given to the edge computing device provided by IMAN. So we are delivering different measurement constants. So one of them is shown here, carbon monoxide, and also oxygen. So what was interesting here, that we were able to see that in this combustion process in the furnace, there was different things happening that were not possible to see before. For example, some changes of carbon monoxide concentrations during some processes, because as I mentioned, the system has a response time of 1 second. And the whole idea is to improve the combustion control of this in this big furnace. So optimize the burner work, and so overall energy savings are expected. as well as the quality of the end product. Because if the combustion is proper, if the gas atmosphere above the steel plates is controlled, then we have also the quality, increased quality of the product. Now switching to the next applications. So from the steel plant application where we use the in situ products, so measuring directly in the furnace. Now we have a second case, which is the woodworking case, or where we actually use the extractive type of analyzers. So I will basically explain what I mean by extractive type of analyzers. It's the same technology, but we are not measuring exactly directly in the stack, but we are first extracting the gas with some kind of probe. Then we have a transport through the heated line, and finally to the analyzer shelter when you have the extractive type of analyzers, which basically is an aspirating analyzer which has a measurement cell inside and also performs the analysis of the gas, but already on the preconditioned gas. And why using this method? Okay, this method is typically much more sensitive to the small amount of molecules of interest. And that's why if you have a very low amount of gas, then this extractive method is preferred. And in our case, we are supposed to detect the acetone and in the ambient air. So basically to monitor constantly the ambient air of acetone. And this analyzer was developed within the framework of the program. So the acetone range was from 0 to 13,000 ppm, which corresponds to in the lower explosion limits, 0 to 50% of lower explosion limit. And we are also able to control the optical transmission. Optical transmission simply means what is the opacity overall in the cell, because apart from the molecules of interest, you also have some contamination due to dust or due to some, say, misalignments. So you always take care that you have to also monitor the overall opacity in the sample. And the challenge here was that the sensor was supposed to be deployed and was deployed in the hazardous areas. So we have prepared the system in the ATEX Zone 1 configuration. In fact, even Zone 121, so for the dust environment, the gases environment, and applying the purge units. So basically, this analysis can be safely operated even in the presence of hazardous gases or explosive gases in the atmosphere. And this has been all certified prior to deployment. So this is a wall type of analyzer. So basically, you hang all the wall, and this is the picture of the analyzer deployed in the plant. So it basically collects the gas from the ambient air and monitors the level of acetone in the atmosphere. So thus you are able to see what is the level of acetone, and what is the risk or hazard for the employees in the area. So looking at some performance parameters, so we have reached the detection limit of 8 ppm volume of this analyzer, so quite low for acetone, because acetone is a very difficult component to measure. And with the repeatability of 1% or below 1% of measured value, as well as accuracy of less than 2% of measured value. System was also equipped with Modbus TCP IP industrial protocol, the same as for the wood, for the steel working case. So we are able to communicate swiftly with the edge computing device or with the DCS. That's quite important also for the communication with the end user. And basically, this concludes my talk. And so overall, we managed to deploy 2 types of analyzers in both cases. And we have obtained quite reasonable or quite decent, better than expected performance parameters regarding the detection limits and repeatability. So I will be happy to take any questions. Thank you.
Thank you, Pavel. Very interesting presentation. Let's see if there is any questions in the room. I think it was quite clear, actually, everything you explained. But just the same question as for Christian. What did multiple projects bring to you? in terms of connections, in terms of maybe exposure to new use cases?
Well, that's actually the very good advantages. If it comes from the technical point of view, so we learn basically how to develop, the multis, how to combine, different laser sources. It's from technical point of view, was a very interesting experience. And if it comes to of course, the exposure to the steel plant industry, that was very, very useful experience for us, because again, even that we provide the analyzers to different industrial areas, by far, the steel industry is the most challenging. That's what we observed. So being able to perform a field test at such a difficult environment, with all the challenges with alignment and with the hot heat around, because not only the process is hot, but the ambient atmosphere around is hot. So we were really able to test, the extreme of our of our technology and show that the systems can operate unattended over now 2 years' time. So this was very useful.
Okay, I see. Antonio, please go ahead with your question.
Yeah, it was a curiosity about if you can measure acetone, does it mean that your solution can be extended to other kind of hydrocarbons or organic compounds, or should each composition be tested? Of course, I understand it depends on concentration and so on, but the main idea of the sensor will be adapted to other kind of similar components or similar gases.
Yes, it's a very good question, of course. So I would say in general, as a rule of thumb, if some components has a fingerprint in mid-infrared, then we can measure it. And in fact, acetone was much more difficult than other hydrocarbons because it's quite very large molecule, so it has quite a complex spectral feature. It's much easier to measure lower, smaller hydrocarbons like methane, ethane, ethylene. Yes, we can do it.
Yeah, I was thinking ethylene in particular.
Yeah. So that's ethylene. Yes, no problem. It's much easier than acetone. In fact, because it has much simpler signature in mid-infrared.
Okay, thank you, Pavel.
Okay.
Pavel, one more question from the chat for you. It's a practical question. How do you keep the optics clean when you put the sensor in the steel furnace?
That's a very good question, and of course there is a solution for it. So we have a special purge system. So we have a compressed air being constantly flown through the optics. So there is a cushion of air, making the separation between the process and our windows. Yes, that's absolutely mandatory.
Okay, that's clear then. Is there any other question in the audience? If not, we thank you again, Pavel, and I pass the word to Anton Garcia from Abraya, the software partner inside Multiple, which will tell us about the computing platform involved. Please, Anton, whenever you're ready, you can share the screen and we'll be good to go. Yeah, just go in the full screen and also don't forget to unmute.
Do you see my screen? Yeah.
Yes.
Okay.
Just
okay.
Put it in full screen.
Yeah. Sorry.
Yeah. Okay. Floor is yours. Thank you.
Okay. Thank you. Okay. As said, I'm Anton Garcia. I'm with Abraya. We are a company working in the development of cloud services for image and video processing. And in Multiple, we had the opportunity to focus on the workflows for the development of machine learning models, which is a problem that we face in our daily work, and specifically because there are of course many solutions for this purpose, but specifically we focus it in the development of machine learning workflows for hyperspectral images, which I think there is many things missing in this regard. So in multiple, the idea was to combine an edge device with a cloud platform, so that the edge device works in the factory floor and operates in real time. The edge device is in charge of real-time data acquisition and real-time monitoring and control operations. On the other side, the cloud platform is in charge of ingesting the HSI data. The HSI data is really heavy, so it's not feasible to ingest this, to store this data locally in the edge device and even in a computer is not a practical solution, and it's not scalable. So here the cloud approach fits very well. But the cloud platform also provides a scalable way to create and manage the data sets and to support an agile approach to prototyping and deployment of classification models, specifically targeting hyperspectral images. Okay, regarding the edge devices, they are physical units, and the hardware is, as already commented by Roy, is an off-the-shelf system on module, which is powered by a GPU unit. And this device, the contribution in multiple in this regard is the software that runs in the device and that supports the acquisition in real time of hyperspectral image and the reconstruction in real time of the hyperspectral data cubes. Also, in the edge devices, the machine learning pipelines required to detect defects, to classify defects, and to perform process monitoring, like, for instance, the measurement of color of chocolate or the grading of its gloss. These machine learning models can run thanks to software that implements the whole image processing and analysis pipeline. And also the edge device is in charge of the real-time process control. There are decisions that are taken based on these measurements and classification outputs. And the edge device has suitable interfaces to convey the decisions to the relevant factory point. So a very important part of the edge devices was the availability of factory-ready interfaces. So something which is difficult when developing an industrial application is usually a painful point is integration in a factory. So in this regard, to have factory-ready interfaces is essential to minimize the effort, the integration effort required. In this regard, the approach adopted in multiple is pivots around the use of OPC UA server for remote control. That can be used both in local network, but also in the internet, allowing the operation of an edge device from a remote location. Also, in the edge device, we have different basic visualization operations specific for HSI data. And of course, the capability of the edge devices have the capability to connect to the cloud using the API. to ingest data and to update the models that run in the edge device. Okay, here we'll see a video with some of the. Okay, in this video we can see. Oh, I think it's not running very well. Well, it's not running very well, the video. Sorry, but it's some images from the boot panel use case. Here we can see how the images are captured and the data cubes reconstructed in real time. Also, there is some basic segmentation here. We can see the basic visualization operations to visualize specific bands or to make zoom in specific parts of the workpiece. And here we see the operation of the OPC UA connection that operates in parallel to the image acquisition and processing pipeline, so that we can change in real time the exposure time as is being shown right now, or the frame rate, and any relevant camera parameter. We can change them in real time without interrupting without disturbing the pipeline, the image acquisition and processing pipeline. The other component of the HSI processing platform is the cloud part. The cloud part is in charge of data ingest and the creation and management of data sets and the prototyping and deployment of models. For this, we have an infrastructure which is basically the cloud storage and a number of cloud microservices, which are based on an HTTPS API, and then open authentication, open authorization, standard. And also the cloud has two different interfaces: a web interface that allows basic interactions with the cloud, and the Python API interface, which allows more advanced operation and supports all the HSI specific operations. The API is released as a standard Python package, and it can be easily installed. And of course, it needs to be operated the use of a secret API key. Okay, regarding the data ingest and management, we have adopted a project-based approach, so that data sets and models are organized in projects, and the data ingest is directly related to specific projects, and the operations that can be performed regarding data and also the metadata is we have basic search operations for both for data and metadata. Metadata can be any information in the, for instance, in the MV headers of an HSI image, or in EXIF headers of PNG image, or other metadata that is added at any point of the image acquisition process and image processing pipeline. Again, the two interfaces can be used here: the web-based interface for basic data upload and for project creation, and the API-based both for generic operations and for HSI specific operations. Going more into detail regarding HSI specific operations, we support, for instance, the manipulation and visualization of hyperspectral images, the selection of specific bands, of course, the extraction of the principal components of a data cube, the intensity of the panchromatic intensity of the data cube, and we can also produce PCA-based pseudo-color visualizations. We also support multi-format, multiple formats, so that we can work both with MB files, with TIFF files, or in the case of multiband image, and with mosaic, with TIFF and PNG in the case of mosaic image. We allow the conversion between these formats. It is straightforward. And also we support the downsampling, the bit depth downsampling, and an interesting capability sometimes is to convert MB or TIFF files to PNG mosaics. Of course, some information is lost, but if bit depth is not that critical, it's really beneficial in terms of image weight and prototyping times. Okay, regarding the other part of the cloud platform, the other function of the cloud platform is supporting the prototyping and deployment of machine learning operations applied to HSI data. First of all, in any machine learning workflow, we'll need data sets, and we'll need training and validation splits. We'll need augmentation capabilities. All this has been adapted to the case of HSI data. We also support preprocessing operations, which need a specific approach with HSI data, like cropping, sample and band filtering, and also other which are not data specific, like sample and category filtering. We support currently both tag-based and mask-based annotations in the cloud. And dataset is the first part is the starting point of any machine learning workflow. But the next step is to prototype models, to train models, to validate these models, to test and validate these models. And here a common problem with HSI image is the lack of model architectures and pre-trained model architectures. So we have tested and implemented some classification model architectures which are ready to be applied to hyperspectral images, and some with pre-trained layers and some without them. And of course, we support the application of fine-tuning and the training from scratch of these models using the data set that we can build with the platform. And an important approach here, which is quite common in machine learning research and development, is the use of Jupyter-based notebooks, because with this approach we can develop quickly, and we can iterate quickly in the development of specific workflows and dashboards for specific applications. We support, besides the training, testing, and validation of models, we also support the storage of models and the deployment of validated models to the edge device. This is an essential function of the cloud part, because otherwise it would be just for research. But the cloud part allows to create a new model and to deploy it to the edge device. An interesting thing that we have seen is that we have focused to build is a dashboard for the conduction of feasibility studies in very short times with no code. And we are quite happy with the results that we are getting in this regard. And as the outcome of the project for us is we are quite happy. We are launching a product which combines the edge and the cloud in a platform for HSI image classification. It is in the initial launching phase. We just have pre-commercial prototypes right now, but yeah, we expect to hopefully to ship the first units by the end of this year. And this is all. If you have any questions, I would be really happy to answer.
Yes, thank you very much, Anton. If you have any questions, please raise your hands. And Anton, actually, I'd like to ask you to say a few more words about this Edge Cloud platform. Who is the target audience? Who should go and check out this website and see if it's useful for their production side?
Well, the target audience is, from our view, is anybody conducting feasibility studies with, in the first place, conducting feasibility studies with HSI cameras, because working with HSI cameras is painful in many regards. There are problems with lighting, there are problems with the camera setup, there are problems with the operation of the camera, and then classification is not aligned with the mainstream, because hyperspectral images have many bands, are not three chromatic images. So I think this platform, which provides the edge with the software ready to acquire and to reconstruct the data cubes, and with dashboards and workflows that can be entirely customized using Python to test classification models. I think it shortens a lot the time of a feasibility study. That in first regard, and of course we also hope to reach integrators of solutions that are looking into hyperspectral image for industrial applications.
Okay. And just to make it clear, so this platform will exist after the project ends, and Brian will keep supporting the clients on this.
Yes, indeed. We have been constantly in the project, and we keep updating the API and updating the workflows, and yeah, we will work in the marketing of the Edge Cloud system, because we think it's HSI machine learning operations in hyperspectral imaging is a niche application which is not well covered in right now, and we see here an opportunity to use our technology.
Okay, that's very clear. All right, so I'm afraid we're running quite tight on our timing. So if there is no other question, I think we thank you again, Anton, and I will pass the word to our next speaker, Jordi Melado Carretera from the Iris Technology Group, who will present us the food production use case in the multiple project. Jordi, the floor is yours.
Okay, give me a second, please. Okay, can you see it well?
Yes, good to go.
Okay, well, here. Okay, so I'm Jordi Mellado from Iris Technology Solutions. I'm the commometrician in charge of this project. So Iris Technology Solutions offers, like as the name says, like solutions based on a spectroscopy, like in general vibrational spectroscopy and also HSI. So for different like kinds of applications, like in the food applications, also pharmaceutical, also textile. So we have quite experience on this kind of different things. So during the multiple project, we have focused in the food case application, which the partner was Jotis, and he has collaborated with us in the project. So the initial goal of Jotis was to provide different food products in order to nourish like the people that was in danger like of getting like not having enough food. Okay, so since then they have extended their product portfolio to different food such as cakes, pastries, beverages, confectionery, desserts, among others. So give me a second. Okay. So many processes are involved during chocolate manufacture, as you can see here in the scheme here in the slide. So we can see that it comes from the post-halving of the cocoa to the transformation into chocolate. So the main steps that we focus on monitoring during the chocolate process was the refining or conching and also the tempering. Also, Ayman has collaborated in this project with Jotis during the gloss estimation. So we are going to focus on viscosity and particle size estimation during conching and also the tempering index during tempering. So I'm going to explain these two processes. During the conching, all solid particles are coated with the fat from cocoa butter, and they are evenly mixed through the matrix, which changes the flavor profile of chocolate. Then the viscosity is reduced thanks to the friction generated in the increase of in temperature during the process. So the particle size and viscosity are important parameters during this step to estimate. And then we have also the tempering, which has the aim in order to provide a good crystallization of the fat crystals, which provides like the shiny thin appearance of the chocolate once it's finished, and it looks more appealing to the customer. So in order to assess this, if the chocolate was well tempered or not, we use the temper index, an equipment with an equipment called tempermeter. So okay. I don't know. It sounds something, but I don't know where it comes from. But anyway, so two different multimodal monitoring systems were integrated for the conching process, which is going to be the process I'm going to focus on. So here we have like the benchmark system that we have at Iris, which is the Visum NIR inline, which works in the near infrared range. It works under the diffusive reflectance mode. And also it has 256 channels. On the other hand, Sonorics, as Christian said, like they have a really small sensor, like which is quite handy and is quite cheap as a counterpart to our sensor. But in the other side, on the other hand, it has only 16 spectral channels, so it has less resolution. So it's a good idea in order like to compare them, which so we can see in which applications which one is better or not. It also works in diffusive reflectance measurements. So for the integration, I know Antonio asked about that. Like the only thing I can say is that for the integration, it was quite difficult for the optical engineer to adapt like the Sonorics sensor to the whole embedded prototype. But I don't think I don't know if you're talking about integration regarding like how it's to integrate this into the process or how to integrate in the whole prototype. Like for prototyping, it was quite difficult, but once it is solved, like the optical engineer like just figure it out. So it's quite easy to integrate both prototypes into the conching process. So what we did is like just to thanks to a bypass system that we have here. I don't know if you can see my, no, you cannot see it. Let me check if I can do that. Can you see that? No. Anyway, so you see here the bypass system in which the two sensors are integrated. So the chocolate flows through the pipe, and then you take the measurements from both prototypes. So the spectral acquisition is accomplished, and then these both prototypes are connected to a PC which has a software, which has the embedded chemometric models or machine learning models in order to estimate the particle size and viscosity. So at the end, what the software retrieves, which is quite user-friendly, is the particle size that we can see here in this slide in microns and the viscosity in centipoise. Finally, these both values are stored in a log file, which can be assessed by the partner or the customer. So wait a second. Okay. So then I'm going to explain a little bit about the results. And I also make a little bit of comparison between the two sensors. Here are the measurements performed by the by Jyotis during the project. So we can see that overall good correlations have been achieved for the viscosity during the conching process with good prediction, also accuracies, and in both of the sensors, like good correlations are achieved. So that's good for both of them. Then for the particle size, we have seen that for the Bizumin line, we were obtaining like good results regarding the correlations in between the particle size that we know from the reference value, which was measured with a micrometer that has Jyotis. And also when we compare to the sonorics, like we can see that there is a worsening of the results. And we kind of explain that because since sonorics has less resolution than Bizumin line, and particle size is a parameter that is quite complex to measure because it has so many, like chocolate has so many different particle sizes. It's not a unimodal distribution, it's like a kind of a multimodal, quite complex. So you need more information regarding this. So in that case, like sonorics, Bizumin line outperforms sonorics, but this doesn't mean that it's a bad outcome. It's like it seems that sonorics would be a good idea, for example, for viscosity measurements in which has a similar performance than Bizumin line, but is a cheaper sensor and a smaller sensor. But in the case of particle size, then Bizumin line, it comes out as an alternative. So finally, for the temper index, like in this case, it was quite complicated to measure like the samples because they had to, like, temper is something that happens so fast. So once you measure it, you have to pull it out of the stage, and like it's something that has to be done quite fast. So it was difficult to take enough samples. Anyway, we have performed several experiments in different days, and we were able to see, like, we were able to discriminate between the samples that were well tempered, like in which like we know that they were well tempered thanks to temper meter, thanks to the temper index, from the ones that were not tempered. And here we have the spectral bands that are related to fats and also sugars of the chocolate. So finally, for the main results, we have made a comparison table with the cross-validation errors. We before have shown the results of prediction as well, but we wanted to do the comparison with the cross-validation values. So here we can see that in the case of particle size, the Bizumin inline works better than the sonorics. And in the case of viscosity, both sensors work in the same, like, at the same level. So in general, we can see that chocolate production can be successfully monitored through the inline measurement of NIR spectra. So the main conclusions also are like the advantages that pose to integrate these sensors onto the process of the chocolate manufacturing. So first of all, you are doing online and automatic measurements. what does it mean is like they don't, before there was a worker on the process taking samples and measuring them. So they had to do several measurements. First, the particle size and the viscosity, which takes time, like even 15 minutes. In this case, you are just retrieving a value in seconds and in automatic mode, like it's stored in a file that they can check. Also, a minimum training is required by the operator. They don't need to know about the insights of a spectroscopy. They just get a value and they can assess that value based on what they know from their process. And then also fast measurements. As I said, like these sensors take seconds in order to perform a measurement. Also, since this is like related to the fast measurements, like if you can do fast measurements, then you can do real-time monitoring. So you can assess during the whole process, like if there is something that is not going well, if you need to change something. What they do in Jotis is that they add lecithin in order to change the characteristics of the chocolate, so they can act accordingly to the values they are retrieving from the software. And finally, good accuracies were retrieved by the models, and also they were discussed with Jotis, and they were quite happy. So that's most of it. If you have any question, please don't hesitate to ask me. Thank you.
Thank you, Jordi. The very exciting part has started about the use cases. Do we have any questions about the chocolate use case in the audience? I'm wondering, actually, Jordi, also, what about implementing the solution in the other type of food productions, also with maybe larger particles, so powders, maybe even things like beans?
Okay, in fact, we have in fact integrated some sensors. Like in that case, were based on hyperspectral imaging. For beans, for example, it's quite promising the results we have. In the case of powders, we work with a similar sensor that in the Bismarck line, and it gives good results for certain powders. Like the thing is that the powder has to be like the difference in particle size, it can pose a problem. So sometimes you have to grind the samples or not, like something that needs to be assessed project by project. And also like some kind of like the most problematic thing that you can have with food samples, if they are, for example, or transparent, like in case of certain distilled beverages in some scenarios, and also with really dark samples, like because the infrared light gets absorbed from the sample completely, so you cannot retrieve a good signal. In the case of chocolate, I know it's brown, but it had a good signal. Like it has to be really dark, like almost black. So that's one of the drawbacks. Yeah.
Okay, that's very clear. There might be a question from Tom Sheffilin from the NASA SPIE. I didn't quite understand the chat. Tom, would you like to ask it?
Let me check. Okay. Is it in the chat? Because I don't see it.
I just got a piece of a question in my private message.
Okay.
All right, well, that doesn't matter. If there is no other question, I think we're also running quite late. So we thank you again, Jordi, for the very nice representation of the achievements of multiple in the food production. And I'd like to switch to the next use case, which is woodworking. And Cesar Taboyas, the head of R&D at Royo, will present it. Cesar, whenever you're ready.
Thank you, Ivan. Ready to start. I will share my screen. Okay. Just a second. Okay, can you see my screen?
Yeah, the floor is yours.
Okay, the floor is on. Okay, let's start. As Ivan mentioned, my name is Cesar Taboas. I am the person in charge for the R&D department, and as a part of Royo. Just to do a very short introduction of our company. Royo is a company that was founded 50 years ago. Our activity
is to produce Bardun furniture. In that case, we have 3 different locations around Europe, two in the northern Poland, and also the headquarters, and also our use case that we are going to analyze in that in the case of the Valencian factory. In that case, just to talk about some figures, we have over 1,000 employees, and we are producing over 2 million units per year. Okay, just to go to the workstation where we have analyzed in the multiple project, we have addressed the case of the lacquering line. Why? Because it is the most critical process that you could find in the furniture domain. So in that case, we have tackled 2 different issues. First, the possibility to improve the effectiveness or the efficiency of the line by reducing the non-quality cost, and in addition to that, some safety concerns that Pavel mentioned before. Just to know how this line works, it consists of 3 different steps. We have like 3 different layers. Firstly is the priming layer. Second is the base one, and finally we coat the finishing layer. After this, we have some kilns to remove the solvents, and finally we have in the outlet the quality control, but today is made by manually. Okay, so talking about the defects that we could find in the outlet of the lacquering line, for example, we could find the presence of dust that is in the ambient, peelings and orange squeen, for example, some air bubbles in the finishing layer, hazing, some sanding marks coming from the sanding machines, and other kind of defects. Okay. In addition to identify the potential defects, another consideration that we took consider is that once we are using solvent-based material, we have some ATEX limitations just to choose the kind of meters that we are going to deploy in the line. In the case of the analyzer that Aeroptic has deployed in our line, the point here is that we use some solvent to clean the machines. So in that case, the concentration in the air of the acetone is quite critical under the legal regulation. So by deploying this analyzer, we have in a real time the concentration of this gas, just to avoid any healthy or safety issues. Just to try to correlate the potentiality to appear some defects, we should consider that we have from the previous projects we have implemented in the past some sensors. For example, which is the temperature in the kiln, which is the humidity in the air, which is the energy consumption that we have in the several machines that is in the line, and other critical variables. But the point here was to switch this information with the data coming from the multiple the meters, which are those meters that I mentioned before. For example, the defects that could appear in the outlet could be present in the pieces coming from, for example, some melamine on some defects coming from the board, or also the humidity or the concentration of steam that is inside of the board. So in that case, we have developed some sensors to measure these critical factors from the raw materials, also from some previous processes, and also in the outlet, in this base layer and also in the priming layer, we have developed some tools to measure the quality of the amount and also the quality of this layer from the priming and also for the base wax. Here we have the analyzer of the acetone, and finally in the outlet we have now the possibility to measure not just the presence of some defects, also a potential difference from the chromatic coordinates. And joined together, we have a global interface to control and to monitor all these different meters. So these the sensors that we have addressed during this workshop. There is not any further points to be tackled here. Okay, and this some example of the dashboard that Anton has mentioned before as well. So the possibility to have the possibility to take decisions in a real time, just to improve this efficiency and also to control these safety issues. Also to have the possibility to be able to trace some problems that would appear in the line, but is coming from the previous processes, and so on. And this is some screenshots, some pics that is also connected with the example that Anton has said before. Today is something that could be repeatable, not just in our factory, for example, for the blacking process, for the vacuum process, for the 3D lacquering lines. Also, there is a very extended lines that could be deployed in other firms on around our industry and business. And that's all.
Okay, that's very exciting, Cesar, and it's also very exciting to have finally a presentation from the actual end user of the overall of the whole multiple solution. So being that, could you give us some feedback on whether this solution is in general was in general useful for Royo, if you plan to implement such solution in the future, if the multiple project gave you some valuable links to the manufacturers of those components and separate pieces of the solution.
Yeah. As I mentioned, for example, regarding the acetone concentration meter, it is quite useful because in the past this was something unfeasible to have in a real time this data. So in that case, it's something to add value for our employees, for our workers. And regarding these tools, in order to reduce this quality cost, is also something very interesting. Why? Because in the case of the kitchen furniture makers, for the bathroom makers, for example, these are some developments that we could deploy in the future for our other factories. For example, in the case of other firms, as I mentioned, kitchen, bathroom furniture, and also for other makers in in addition to that, Ivan, I guess that these solutions could be deployed, for example, for tiles, for example, for 2D ceramics or other businesses.
Okay, yeah, that's a very valuable feedback. Anyone else? a unique opportunity to talk to the end user. Also, the partners of the projects, feel free to raise any questions you might have. Cesar, so will you continue using this kind of solution in the future at Royo?
Yeah, yes, this is our intention. For example, in the case that we have compared the results from the cameras that we install in the multiple project, compared with this manual action that we deploy in the outlet, is as we also address in the food use case, we have a very accurate results. And so you also could reduce the fatigue. For us, is something very, very practical for the future. So our idea is to continue developing this.
Okay. Yeah, that's very nice to know by the end of the project. Okay, thank you, Cesar. We're running short on time, so I'd like to pass the word to our last speaker, Luciano Dominguez, the representatives from Rusula, who is managing the steel production use case inside Multiple. Luciano, hello. Yeah, good to see you. Will you be able to share your presentation?
Okay, I guess now it's sharing. Could you see it?
Yeah, yes, okay. Just put it in the full screen mode.
Great. Then 1 second. Okay, here we go. Okay, thank you all for joining us today in this workshop. I'm Luciano Guerra, as Ivan said, and I'm going to introduce the steel production use case in the project Multiple. First of all, I want to introduce a brief introduction of general info of Rusula and myself. Rusula is a global engineering company that works for steel producers. We have more than 35 years of experience in this sector, and we have already performed more than 1,500 projects. Between them, we have developed projects of rolling mills, automation for steel plants, roll pass and operation services, and water solutions for steel sector. Talking by myself, I'm an electrical engineer. I've been working in Rusula for 18 years. I started my career like process engineer in the beginning of my career in Rusula, and in the last years, I have been developing the role of research and development director. Talking just about the presentation, the agenda for it is going to be to talk about Laminoir de Land, to make a brief introduction of the company, to talk about the process of the rolling mill, a brief overview to understand how the steel is produced there, to be focused on the application points of the multiple project, and at the end, we will talk about the benefits and conclusions of the project. Well, Laminoir de Land is the latest European rolling factory. It's a greenfield project, as they say, in Tarnos, France. It's a rolling mill that started its operation in the first quarter of 2018, and they produce heavy plates. Well, the plant, it was really an old plant that was not commissioned, and in the last years, the Spanish company, Hierro Sañón, with the help of the engineering services of Rusula, made the final commissioning and start this plant in the first quarter of 2018, as I said. The capacity of the plant is 500,000 tons per year, and the factory takes a 20,000 square meters factory. All of this in an industrial site of 10 hectares. We produce heavy plates with a thickness from 8 up to 150 millimeters. We can make an idea of how this can vary, with a width of a maximum 3.4 meters and with a maximum length of 24 meters. You can see a corporate video where the process can be seen clearly. Well, as we said, we produce heavy plates, and another option is to produce hot rolled slabs, but this is a semi-finished product. It's not a product that goes all through the process. And in the heavy plates products, we have different qualities for different uses. For structural steel for pressure vessels, for shipbuilding steels, tempering steels, steel for pipe and tubes, and warrior resistant steel. This is all the qualities that we produce. If we talk about the process, I'm going to talk following the route of the steel from the raw material to the final plate. We will start in the heating furnace. In the heating furnace, we increase the temperature of the steel from the room temperature up to 1,200 Celsius degrees. And this is the temperature more or less where the steel is ready to be rolled. After that, we send the slab to the rolling mill, and in the rolling mill, we are going decreasing the height of the slab up to the final height that we need for the final product. We can use several passes, and for each pass, we can reduce more or less 20% of the height. So we can, depending on the initial height and in the final height of the final product, we have to use more passes or less passes. In the final area of the factory, we have a hot leveler, a shear where we put the head and the tail of the plates, and a cooling table and a dispatching area. Here we can see a diagram of the rolling mill. We start with the slab with the steel in the reheating furnace. We go through the descaler where we send or inject water at high pressure to the steel to remove the scale. A rolling stand, as we said, we manage the height of the steel. A flattener to calibrate the tolerances of the final product. A shear, a cooling bed, and finally the customer length area. If we talk about the application points in the reheating furnace, we introduce 3 gas analyzers in the furnace. We introduce a SWIR camera. In the rolling mill, we introduce a dual band camera and a visible camera to measure temperature and to detect mixes to see the quality of the steel. And in the final area, we introduce a profilometer or a 3D camera to measure the height of the final product. If we go one by one, in the reheating furnace, we introduce 3 gas analyzers strategically located in the middle of the different heating zones. This is because we want to measure and to manipulate the control zones of the combustion in the control zones. The provider is one of our partners from Poland, is Air Optic, and we can measure temperature, oxygen, carbon monoxide, CO2, and water as well. The intention to use this gas analyzer is to reduce the scale formation, playing with the internal ratio between the air and the gas, of course, always maintaining the global stoichiometry in the whole furnace. At this point, all three gas analyzers, are fully installed with the DCS system, installed and integrated with the DCS system with our PLCs. The information is recorded by Modbus and by TCP and by web server as well in a record server from Air Optic. And we plan to validate the other records of the furnace, comparing with these records to predict the internal behavior in the furnace, because some of the values of the process are not really well defined. The camera inside the furnace, we have a dual purpose. We can see a video, but this video is the actual camera. It's not the new camera of the project. I will explain later why. We try to measure the temperature of the slabs before discharging. This is really important. And in this case, regardless emissivity. As well, and this is the point, we have to allow the control in the discharging movements, because this movement that you see in the video is a manual movement, and the operator have to take a clear scene of the slab when he is manipulating the slab. The camera and the application was developed by Amen with a camera from Photon Focus. All of them are partners in the multiple project. And we performed tests to validate the technology, and the technology was validated perfectly. But we can see here the main problem, that the quality of the new camera, you can see in the left the new camera, and we can see as well the temperature that the new camera is measuring, but the resolution is not good enough to making operation. So this at this point, the camera is not installed, but maybe in the future could be an option to introduce in another hole in the furnace, but not to substitute one camera for another. In the rolling stand, we introduce a dual band camera. The idea of this dual band camera is to detect or to measure the temperature of the slab before entering the rolling mill, because of metallurgical issues, we have to take a clear idea of the global temperature of the slab, and of course to measure as well the quality of the steel. Not really the quality, but the difference between the different families in the production line. This is to avoid mixes. If we have a mix because of a misunderstanding in the tracking, if we have a mix with the final product, then reject could be appear, and we will be able to lose a customer. And this is something that we have to avoid. The dual band camera is a camera provided by Photon Focus, and the models that are running inside the camera have been developed by our partner IMEN. Both models have been tested in a lab and as well in the plant. And the actual integration we have already connected to the PLCs, and we have already integrated with alarms if a mix detection. If a mix is detected, and of course we send as well the temperature of the slab for each pass. As well, we have a camera in the exit of the rolling stand, but the idea is just to measure temperature, because here we don't need to check if any mix, because the rolling has started. At the end of the rolling mill, after the flattener, we have as well a profilometer, a 3D camera, and this camera will help us to make an individual profile for each plate. This is a quality footprint of every product, and will help to make a better tracking for each final product. The resolution here is up to 2.1 millimeters, and this is good enough for our customer to give certification of quality. A special housing has to be developed to support these high temperatures. You can see here how the slab is going through the camera with it's hot, it's really hot, and we have to develop as well a pedestal to measure all the families of all the widths in the production line, depending on the field of view of the profilometer. The housing was developed by IMEN, and the support was developed and built by Laminoir Deland. In this point, with this in this application point, the technology was validated. We have a POC successfully. We improve safety because here the measurement is done by operators manually, and we increase the quality and traceability for each measurement, because the measurement is made every time with the same resolution, because it's a machine, it's not a operator who is taking these values, and the traceability because the measurement is related with the tracking and the identifier of every product. Well, just to finish, we talk about the benefits of the application points in these projects, and we can talk about the analysis, the gas analysis, that we can measure the air and gas ratio for each combustion zone, so we can try to reduce the scale formation inside the furnace, and this at the end means savings, and we can optimize the combustion control. These are related because this means savings. If we optimize the combustion control, we can reduce the scale as well. So the idea is to close the loop with these gas analyzers. In the rolling stand, the idea is not to have no rejects due to quality mix, because the detection of different qualities with the cameras, and we have to have a high precision temperature measurement because, as I said, this camera can measure the temperature independently of the emissivity, and this is something different of the actual system that is use pyrometers that have to use a parameter to modify the emissivity of the steel. And of course, the thickness quality control can help us because the control for all the final products, not just ones. And we can improve the safety solution because the people that is measuring there can be just take the information from the profilometer through the SCADA. All this data recorded in all the application points regarding the multiple project and other information sent from the PLCs have been updated to the Monon Cloud, and the operators and managers of LDL can access to this information and to see the actual KPIs and to see as well the trends of a particular variable. Well, and finally, our conclusions is that all technologies were successfully validated. Everything was working at least in lab or at least once in plant. We have the idea that the improvements in robustness and easy maintenance is a pending point for the technology providers, because we are in a plant that is working 24/7, and this is important for the survival of these equipments. All the applications are POC, and the next step, in our opinion, must be to develop equipment for industrial environments, because some of them are fragile, I will say, for these environments. According, of course, with the customer requirements, that is sending their reports to the providers. And that's all for my side. Of course, if any question, please let me know.
Thank you for this nice summary, Luciano. There are, I'm sure, a few questions already. I have a few, and the first question actually comes from Andreas Schick from Heft System Technik. He's asking about the 3D camera. What kind of camera you employ?
It's a profilometer. It's a commercial profilometer, and I have no the real information because the provider is IMEM, but it's a profilometer that is connected to each device.
Okay, yeah, exactly. So that was my question about the importance of having all those sensors connected to the edge devices and then plugged into the cloud platform. Can you say a few words about that?
Yeah, for us it's important. It's more important even to the cloud to connect to our DCS system, because we have all the information of the new devices recorded in our servers. So we can record this information with a cycle of 100 milliseconds. So we have a lot of information and new information in our servers. Thank you to these new sensors. We have really interesting records with the gas analyzers that we have to validate and to study with Pavel and with the air optic people, because this, how can I say, this take note of that something is happening inside the furnace and we have no control of it, and with this analyzer we can understand what is happening inside.
Right. That's what I was thinking. So physically accessing all those furnaces around the world, I can imagine you have customers for Brussels all around the world, might be challenging. Do you foresee implementing these kind of solutions at other steel manufacturers?
For sure. This is if it works fine and we solve the problems of maintenance, because there are some problems of misalignment when the furnace is going down in temperature. If we can solve these issues, we have a powerful tool, because we can measure what is happening inside the furnace, but not in the end of the furnace. We can measure inside the furnace in the control zones. where we want to actuate. So for us, it's a new business unit for sure, and I believe if Aeroptic is ready for solve these problems, we will be able to open a big business here with the heating furnaces. We can understand the huge amount of energy of a reheating furnace is wasting every month. We can talk about hundreds of thousand euros. So okay, if we can reduce 1, 2, 3%, we can make a return of investment in a few days or a few months for sure.
Okay. So the multiple solutions does create multiple business cases for you for future.
For sure. Yeah.
Okay. I think this is a very important feedback for everyone involved in this project. Okay, thank you, Luciano, for a very nice presentation with a lot of video footage also. That was very exciting to see for all of us. And with this, actually, we're coming to the end. Let me just share a little wrap up with you. So this was the multiple workshop, the project devoted to multimodal spectral sensors and orchestrated deep models for integrated process optimization. So we have heard exciting presentations today from Roy Mendes from IMEN, from Karsten Schneemann from Photon Focus, as well as presentations on spectrometers from Christian Kerner from Synorix, Paul Luksinski from Aeroptics, Anton Garcia from Abraya, and Jordi Melado Carretera from Iris, Cesar Taboyo from Royo, and Luciano Dominguez from Rusala. So I'd like to thank all the speakers of today's session again very much, as well as all the other project partners involved in multiple. And the very important message here is that so the project is very much looking forward to have your feedback. So don't hesitate to connect to us via email or website, www.multipleproject.eu. We're also present on LinkedIn and Twitter. And if that's not enough, you are also welcome to reach out to us about this project through the EPIC platform, which I represent. And with this, I wish you all the best for the rest of the day, and see you soon on the next occasion. Thank you.